Now that we know what KD trees are and how to build them, let's talk about why they're useful. So fundamentally, their usefulness comes from the same idea as the quad tree, where each object or each node controls several subspaces. Now in a quad tree, it's 4 subspaces, one for each of your 4 children, and in a KD tree, it's basically the same thing, except you only have 2 children. So each node is in control, or is the boss of, 2 subspaces. So for example, here D, it is in charge of the subspace below and above it. A is in charge of the subspace to its left and its right, and so forth. So depending on if you're in an X node or a Y node or a Z node, if you're going into higher dimensions, you'll be splitting the universe in half along that dimension. Okay, so now let's see how we can use that space splitting idea to implement one of those space-related methods that I mentioned. So in the quad tree demo, we talked about range finding, the idea of finding all of the items that are inside a rectangle. Now we're going to do another problem, known as a nearest, where we want to find the closest point, just like the space horse earlier. So this point is 0, 7, and out of all the points, you and I can tell, out of A, B, C, D, E, F, E is the closest. However, the computer doesn't know that. It can't just look at this diagram, and instead it's going to have to start at the root and traverse this tree in some sort of intelligent way. So I'm going to walk you through a KD tree traversal, and then I'll give you some pseudocode for how this nearest method works. Now this is going to be the main, most difficult part of Project 2B, so make sure to pay close attention, pause the video as I work through it, and maybe rewatch it a couple of times if it didn't make total sense. So let's start by calling nearest on the tree rooted in A, and we're looking for the point 0, 7, right here. So currently the best known point we've seen is nothing. But now that we're looking at A, we may as well compute the distance from A to the query point. So that is just a little, we just measure the Euclidean distance. So that's the square root of 4 plus 16. 4 because 0 minus 2 squared is 4. And 16 because 7 minus 3 squared is 16. So the square root there is 4.5. And that's our distance. So 4.5 is better than infinity because we didn't have any point before. So we're going to use that. I'll record that A is our new best. So we're not done because there may be other points that are useful. So the first thing we're going to do is we're going to think about which side of the tree is the good side. Okay? So we need to consider our 2 children, left and right. So if your goal was to find a good answer as fast as possible, what makes more sense, looking on the left or looking on the right? Well, it turns out, as you might imagine, it's the left side. So we're going to consider the left first since the query point is to the left. In other words, query.x is less than a.x. Okay, so we look on the left and we compute a distance. So the distance is 1 plus 4 square rooted, so that's 2.2, and that is better than what we had before. So we're going to write that down and say our best is 2.2. Now again, we need to either look up or down. So which one should we look at first? What's the right direction to look? So of our 2 children, down and up is the better choice. And the reason is that the query point is to the up. It's the direction that is closer to the query point. Now this is a really important point because in naive implementation, you might always use this left link as opposed to this right link or whatever you know, left slash down, right slash up, same idea. So if you always use the link that's physically on my screen to the left, you're not going to get as efficient an algorithm as if you go use this correct link first. Okay? So this is a really, really important point. Your code's going to be much slower if you use the link that you always think of as left before the right one. You need to go in the direction of where the query point is. And the intuition is that you want to explore the good side of the space so that you can prune the other side if you don't need it. Okay? So we go to the upside and it turns out it's just null anyway. So all that thinking carefully ended up being a little silly because we got here and there was no up point. So now we go back up to E, and we've now just finished exploring the good child. We've explored the good side. And now, and this is the last kind of tricky part of the algorithm, we have to ask ourselves, could there be something on the bad side of the line? So we've looked on the good side, the side that could be an improvement over E just clearly. And now we ask, could something down here be useful? So the way to think about this is, imagine the best possible point that could be on this E dot downside. Where would it be in this space? Well, it'd be right here. This is the best thing that could possibly be in the E dot down, just maybe infinitesimally below E, but right below 0, 7. So what's that distance? Well, it's just 2. The way you think about that is it's just the query point's y-coordinate minus E's y-coordinate. Or in other words, you imagine this point here that would be 0, 5, okay? But I wouldn't think about it that way. I would just say the query point's y minus E's y-coordinate. That's 2, okay? And that's better than our current best of 2.2. So if you didn't fully follow that, that's okay. We got more examples coming. So basically at this point, we know that it is worthwhile to continue exploring on the downside. So let's go. So we go down there, and what do we find? Null. Okay, well, kind of a moot point, but we made some decisions to go look, and it turned out there was nothing. So now we've explored both sides of E, so we're going to go back up. So when I go back up, I'm now at A. I've finished exploring the good side of A, everything that could be, that was on the left side of A. So all points to the left have been explored, and now we say, is it worth it even looking on the bad side of the line? So here again, try and imagine what is the best possible point that could be in A's right-hand side. So out of all this, what's the closest point to the query point? Well, maybe A has a right child, maybe not the immediate right child, but some descendant who's right there. That would be the best thing. And actually, it's that same calculation as before. We're doing A.x minus query.x. Okay, so what's A.x? 2. What's query.x? 0. That distance is 2. So 2 is better than 2.2, so we need to go exploring, because maybe there's something there. Okay, so let's go. So we go to the right, and we find out, oh, well, it's just B. B's way far away. Okay, so it's 6.4 in distance. That's way farther than 2.2, but that doesn't mean we made a bad choice, because we have not explored all of A's descendants on the right-hand side. Maybe there's still something over here. So B, having now explored or calculated its distance, we need to either go down or up. So what's the good side? Okay. So the good side is going to be up, and the good side, it is always worth exploring because it's more in the direction of the query point. So if we go up from B, then there's going to be potentially something useful up there. So we go up, and once we get there, we end up at C. Okay, C's distance, it's not as bad as B's distance, but it's not an improvement over 2.2. So once we get to C, we calculate its distance, which is 4.5. And so now we need to consider C's two children, left and right. So which side's the good side? Well, it's left. So something over here might be better. So we go straight to D, and we calculate its distance. Well, it turns out it was actually worse. So just because you're moving towards the good side doesn't necessarily mean you're going to get an improvement, right? We went from 4.5 to 5, but we don't know until we look. So now we consider D's children. So which side's the good side of D? Well, it's up. So let's go check it out. So we go to up, and it's null, so we're just going to return. We're done with that. So we're back to D, and now we ask ourselves, do we need to look at the downside? Okay. So the downside, in this case, okay, think about what is the best possible point in this little subspace that's below D, so D's bottom subspace. Okay, so it turns out that it is not worth looking, because the best possible point would be right here in the corner of this box. Okay, so that would be bigger than 2.2. Now at this point you might get a little worried, thinking ahead to trying to implement this thing, and it might seem maybe a little tricky to compute the distance from a point to a rectangle. It's not so bad, but I'm going to give you a little optimization that'll make your life a lot easier. And that is, you can just measure this distance. So rather than measuring the hypotenuse, you can measure it to this splitting line, assuming that it extends infinitely. In other words, we just compute goal.y minus d.y. And effectively what's happening is we're being less aggressive with our pruning. So in a sense, if we use this wimpier green rule, we might sometimes look at a bad side that has no possible better points. But the resulting answer will still be correct. So basically by using this green line, you might occasionally explore a space that has no answers for you, but it's not going to be much worse, and the code will be easier to write. Though you're welcome to write the code that does this exact rectangle version, and then you might expect to get a little bit better performance, but not by much. Okay, So the punchline though here is that there's nothing in this blue space that could possibly be better than our current best, which is E. So we're going to ignore it. So I'm saying good and this bad. Okay. So in other words, we have now basically said that the up space is now finished. It was explored. It was null. But this one we didn't even bother looking at. So we don't know it's null. And it could have been many things. I mean, it might seem a little silly to prune a null because that's going to be instant. You just go look and see if it's null. But this could have been huge. I mean, it might have been an entire gigantic subtree. And so by Xing it out, we don't even look. So now at this point, we're done with D, so we go back up to C. So now we ask ourselves, we've looked at the good side of C. So right here, that was the left of C. And so now we ask, could there be something better on the right side? So what's the best possible point that could be on this right side? Well, it's right here. And that is worse than distance 2. So again, we're going to prune this. We're not even going to look at D's right child or any of its descendants. We're just going to give up and say, I know there's definitely nothing over here that's better. Okay. So now having handled C, we're going to go back up. So we've gone the left and the right of C, so we'll go back up to B. So we finished the up side of B, which was B's good side. And now we need to think, now that we're back to B, do we need to look at its bad side? Okay. So the bad side of the line, we check and we say, what is the best possible point that could be here? And that distance is bigger than 2.2. You can either use this exact amount or use the line in green. Now Google Slides has made this look uglier than it does in edit mode. Look, that's perfect. Anyway, all right. So the line in green, you could use that instead if you don't want to do this trickier computation. So now you've finished B, so let's go back up to A. A has explored its good side and its bad side, so we go back up. And at this point, we have found an answer that is guaranteed to be correct. And every dashed link, or the ones that are X'd out, those are unexplored. We didn't have to look at them, and it's guaranteed that nothing below those will give us a better answer. So this is the formidable and tricky KD tree, but it's really not so bad once you've thought carefully through all of this example. Now if we look at what happened, we'll notice that for some nodes, we looked at both its good side and its bad side, and for some we pruned off the bad side. And it's all just a matter of how the algorithm lines up. And so what's interesting is that if we move this query point, like let's say we moved it a little further over to the left, we would have actually pruned this bad side off of the A query, or off the right side of A, and we would have been done super quickly. So that's the intuition behind why it's really important we look at the good side before deciding whether or not to even look at the bad side. Okay, so that's it as far as this demo, and so let's see a little bit of pseudocode.